Yeah, so week 7, halfway through the semester. I hope you guys are not overwhelmed with work. Attendance has started to sort of drop off in my classes. Hopefully today, everyone that's not here is at the career fair slash internship fair. Um, but you guys should definitely be working on your learning portfolios and hopefully doing that as you're taking notes and trying to put that together. Your learning portfolio check-in is in the early part of October. September is almost over. So you've got a couple weeks, something like that, before your learning portfolio check-in. I'm going to make that participation credit for that week. And remember, your learning portfolio is a big part of your grade. So for those of you who are, just watching me lecture or just staring into space while you listen to the sultry sound of my voice, for whatever reason you're into that, you should be taking notes. And I'm going to be looking at that at the end of the semester when you turn that in to determine how well you understood the material in this class. And, that's a decent sized part of your grade. So, and people have been turning their cameras off. So unless you have debilitating anxiety, let's see some cameras on. Let's see some faces. Even if you guys aren't paying attention, I don't like lecturing into the void. So if you don't care, turn your cameras back on. That's been another common thing in my classes. Thank you. I like to see that you're here, and I can try to judge based on how bored you look, how much time I can spend on each topic. So, and whether or not you guys are sort of getting this stuff. So does anybody have any questions on anything? How's your semester going? Are you guys making it through okay? I see some head nodding yes. You don't have anything in here for a couple weeks, but don't wait till the last minute to be looking at your learning portfolio. And you have an exam coming up in the first part of October as well. So, you can sort of be efficient in studying for your exam and start looking at the notes in your learning portfolio and making notes on how well you're understanding that stuff. And at the same time, study for that exam. I think I saw a lot of really good work on your practicums so far. I'm really happy with a lot of them. Some of them are not so great, and I think that some people didn't expect me to grade that stuff as hard as I'm grading it. So this is not a work-laden class, but that being said, you still have to earn your grade in here. So being that the exam is open book, open notes, and you're going to have multiple attempts, your exam is going to be hard. So study for it. And if you're looking through your notes and you don't understand something that you wrote down, or you don't understand one of the concepts that I went over, email me and let's talk about it. I've been meeting with students all semester who are doing that, and talking one-on-one, talking through this stuff is a good way to try to get a grasp on some of these concepts. If you're not getting them, just listening to me talk at you, please email me. I am available to talk. So all of that being said, we'll go ahead and get into our lecture. There is a quiz that's open today. So we have 2 quizzes this week, and they are open until Sunday night at 11:59. I gotta stop talking for a second though, because I can't multitask. And if you're not really sure, if you need help on ideas or formatting or anything like that on your learning portfolio, like I said, that's a big part of your grade in this class. Meet with me, let's talk about it. I'm always happy to meet with you guys outside of class and talk through stuff that you're not sure about, or give you feedback if you want me to look at that before we do the check-in. I'm not going to be grading it super hard on the check-in. It's just a check-in, but it's going to be a participation credit for that week. And if you don't do anything, I'm not going to give you full credit. So, I really don't like giving people bad grades. So please don't put me in a situation where I have to do that. Everybody see me drawing on the PowerPoint? Cool. So we're back talking about water control. We were talking about this last class some, and we'll hit on the high notes again really quickly as we get into this stuff. So some of the things that we need to understand to design and properly install our water control and to have a good water control layer. First of all, our water control layer is the most important control in our building. That's one of your quiz questions. That's, pretty easy one because we're talking about water, right? So, our rain control strategies include deflection, drainage, and the other two of those, drying, and then those are the 3Ds from your book, and then we add in durability because durability is a key factor in having good water control. If our water control layer is not durable and it fails too early, then it's sort of a moot control layer. So a couple other things, we need to know how moisture hurts a building and how moisture moves in its liquid and vapor form. So again, we create a lot of our problems, and windows are a key area where we find those problems. Stuff like this, wrapping our drainage plane into the house, into our window frame is not good. And we saw in that video some of the benefits of doing that cut differently, not using the X cut like in this instance probably, but using this eye cut down here. And that guy talked about the drawbacks of wrapping this part of the drainage plane into your house, but it's easier to get away with that, but rather than something like this, or wrapping this part of the drainage plane into your house and having your subsill flashing attached to nothing but your house wrap. That's not a scenario that's ideal. So again, we're thinking about the building as a system and how some of the changes that we make in the building can give us problems in other areas that were unexpected. When we add air conditioning to our homes and we wrap them more tightly, but we have stuff like vented crawl spaces, we have warm, humid air coming into our crawl, we can get mold and stuff like that. And that insulation, that subfloor insulation in your bays under your floor acts like a sponge and can sort of hold that moisture up against the subfloor, and you can get mold growth and you can get rot. And those are two things that you don't want to have happening in your home. And so, in order to have adequate water control, we need to understand the 4 primary ways that water hurts a building. And we need to understand that whenever you have an issue with water, there's likely a number of water transport methods happening at one time. It's usually more than one way of water movement in your home that's giving you issues. And one of the most prevalent things we see when we start to look for water damage and water issues and humidity issues and stuff like that, we get surface mold. And when we don't ventilate our buildings properly and we don't exhaust the air out of areas where there's high moisture content, like in your bathroom when you're taking a shower, you know, that all that steam in your shower is, you know, through diffusion is working its way into the materials in your bathroom. So that's something that we have to think about. And we have to exhaust things like humidity, or, you know, we have to dehumidify through some means to control that stuff. So if we have a wood moisture we have relative humidities and high temperatures, over 80% relative humidity in the air inside of your house, or we have a wood moisture content of 18% or greater, you're going to start running into issues with mold. And remember, we can use this wood moisture content meter and check and see if we're at risk in having issues. So this is where we got in our last class. So, you know, freeze thaw is something that's common around here when we don't properly detail drainage and stuff like that in, you know, you can have freeze thaw on a masonry facade, on, you know, you can have aesthetic damage, or you can also have structural damage. When you have structural masonry, you can have big issues. So when a material is nearly saturated and there's a sharp drop in the temperature outside, you know, typically below 20 degrees Fahrenheit, and your materials are saturated, it's going to freeze and it's going to expand. It's going to break the bonds in that material and at the material joints, and you're going to start running into issues. And, you know, here, this looks like just aesthetic damage, but, you know, you can have structural damage. You can have freeze and thaw that affects the structural integrity of construction assemblies, and you can have failure, structural failures, and then you can run into some really serious issues. So we see this a lot in sidewalks and masonry walls. And, you know, this is something that we have to design for. We have to make sure that things can dry out and can drain properly, so that we don't run into this issue. And so we, you know, another thing that we have in our buildings is fungal decay. So when it's warm and we have over 28% moisture content in wood, you start to run into things like fungal decay. So this takes a while for this to happen. You have to have high relative humidity at 95%, and you have to have oxygen. So if something is totally saturated and oxygen can't get into that material and work, it can slow down fungal decay. But you know, you walk around in the woods and you see all these trees and stuff in the woods, they're not rotting, they're still standing, right? When we cut trees down, they're wet with sap and moisture and stuff like that. Wood can get saturated and dry out, and it's totally fine. You know, after a rain, you can go into the woods and look for sticks that are propped up off the ground, that are sort of shaded under or sheltered from the rain a little bit. You can find wood to start a fire if you know where to look. You know, wood can dry out and be just fine. So, you know, I've got ghosts. Total saturation will, like I said, will slow fungal decay. And, you know, we're good at creating these situations in the real world, in our houses where we have constant high humidity levels, like in our crawl space. There's bacteria and other junk down there and stuff growing, and but this is difficult to do in a lab. So, you know, when you have a situation in a crawl space, like we've seen a number of times in this class now, the subfloor is like staying really wet, and that insulation's holding moisture against the subfloor up in those bays, you know, you can run into this issue pretty easily over time. Dog's going to inspect the ghost situation, so stand by, I'll let you know what she finds out. So, you know, another way that moisture can hurt a building is corrosion. So you think of this in coastal areas where there's really high levels of humidity, and, you know, there's a lot of salt and stuff like that in the water in coastal areas. But we also see this in climates where it's cold and it snows a lot. You have a ton of salt on the roads. So if you go to Avery County, or if you live in Avery County, they salt the crap out of those roads. So, 2 or 3 or 4 or 5 years of driving in those conditions, the undercarriage of your car is completely toast due to the high levels of salt that they use on the roads. So when you have sidewalks and structural masonry and concrete and stuff like that, metal reinforced concrete, if you don't specify the right type of reinforcement that is designed to resist corrosion, you can run into serious issues with this. So you get water in your concrete and freeze and thaw and it cracks, and then water works its way into your metal reinforcing, and maybe you get some salt in there. You can run into really serious issues really quickly. When metal corrodes, it expands. You've probably seen rusted rebar. It sort of swells up a little bit and becomes brittle and starts flaking off. So when this happens, rust is a current. So it's going to travel through that metal, and it's gonna rust everywhere, and you're gonna start having issues, and your concrete's gonna crack, and you can have structural failures that way over time. So this is not something that we want to see. So the different ways in which water moves, we have 2 forms of water that we have to control for control the movement of in our buildings. We have liquid water, and then we have water vapor. So a couple of ways in which we have liquid water moving through our house. We have bulk moisture flow. We have things like rain and flooding, and we have plumbing. Our plumbing has water in it. So when you have a pipe freeze and burst, when you don't winterize your home and you leave it and turn the heat off, you have a pipe freeze and burst. You can have large amounts of water coming into your home and causing damage in your home. So another way that water moves, bulk moisture, aside from bulk, is capillary action. So water is a polarized molecule. It's got a very positive side and a very negative side. So we have hydrogen, 2 oxygen, whatever that is. So it's got a very positive side and a very negative side, which means that water is unique in that it's really hard to get those molecules broken apart. So we have to put a lot of energy in when we heat water to get it to boil. We have to put a lot of energy into it to get it to get those bonds to break. So that being said, in capillary action, if you guys remember from your high school chemistry class or whatever, you have a beaker. The surface of water does not sit flat. It forms what's called a meniscus. So the water is creeping up because of the nature of its charge. When it touches the surface, it sort of creeps up a little bit, and then in the center you have gravity pulling down, and then the charge of the water molecules on the side pulling up the side of that beaker or whatever you're looking at. So this is a meniscus, which is a curve in the surface of a molecular substance. Here we're talking about water, obviously, when it touches another material. So when you have this with water in a cylinder, this is what it's going to do. A meniscus forms, and the closer these surfaces get, the higher your water gets. And so the less force of gravity is acting on the overall surface area or whatever. So you have gravity pulling it down, and it creeps up. It will creep up the sides. When those surfaces are really close, it can travel. And so water can move a long way through capillary action. And so when you have things like a poured slab over gravel, which is on grade, on dirt, and you have no moisture barrier, water gets pulled up through capillary action, will get pulled up into your slab, and it's not good. And can saturate your slab and then work its way into your house. Remember, we talk about energy and air and moisture. Energy travels from higher concentrations to lower concentrations. Air travels from areas of higher pressure to areas of lower pressure, and with it humidity that's in the air. But moisture wants to travel to areas where it's less concentrated. So, capillary action is, a big deal when you have really moist soil and you have high humidity in your environment and stuff like that. You definitely need a vapor barrier down when in a lot of assemblies, floor assemblies, stuff like that. And, in your crawl space, you guys have probably all seen clean space before. You want to control the flow of moisture from the ground to the inside of your house. So, like I said, with capillary action, when these surfaces get closer, the water will rise higher and higher and can travel long distances, upwards long distances. So a couple ways vapor can move. We have air movement, right? When we have high humidity air, and we have air movement, that high levels of humidity are moving with that air. You can move a large quantities of moisture this way. So remember when we looked at the psychrometric chart and, we're talking about cooling, when we're cooling, a lot of the time we're dehumidifying. That's one way that we control humidity in the indoor environment. So on our psychrometric chart, we have the dew point and we have this temperature here. And as we cool down, when we hit the dew point, we continue to drop in temperature, but we're also dehumidifying when we're at the dew point. So that's how we control that moisture inside of the building. We just cycle the air through the system and the humidity travels with the air. So, all of this stuff is related, and I hope that you guys are getting this as you're taking notes and thinking about all of the things that we're talking about all semester and going back in your notes and, in terms of your learning portfolio, looking at the interconnections between these different things that we're talking about and how they work together and working on your understanding of buildings as a system. That's the thing that you need to take away from this class, is how all of this stuff is related. So back to water. Like I said, you can move large amounts of water in a building through airflow. So another way that vapor flows is through diffusion, which is the tendency for water vapor to fill the space that it's in. So, a gas has the tendency to fill up whatever space that it's in. If it's the same weight as air or lighter than air, if it's more dense or heavier than air, then it's going to sort of fill in at the floor level. It's not going to, be buoyant and raise above the air, but it still will fill whatever cavity it's in or whatever structure it's in. And moisture, vapor, water vapor and air are mixed together and they have that same tendency to fill whatever space they're in. So, a gas, everything has kinetic energy, right? Unless it's at absolute zero. Everything has kinetic energy, everything's vibrating, and when there's nothing to impede the movement of that gas, it's vibrating and those molecules are bouncing off of each other and spreading out. So eventually, that gas is going to fill the space that it's in. So when you're in the shower and you're taking a really hot shower for 20 minutes and wasting all of that, that hot water and that energy, but it's nice because you like hot showers, you're filling your bathroom with vapor. And through diffusion, that vapor is working its way into your walls if you're not exhausting that warm, humid air out of your bathroom, and that will work its way through your house. And when your house is old and the control layers aren't done properly or whatever, you can start and your HVAC system is not designed like it should be, you can start having surface mold and other issues like that. So we said in previous lectures, in the last lecture, I think it was, water vapor can pass through what we think of as a solid surface. Water vapor can pass through wall assemblies. Water vapor can pass through sheetrock. There are microscopic molecular pathways in these materials that water molecules can move through. So water vapor can pass through what we think of as solid materials through vapor diffusion. This happens a lot, and it can be a big source of problems in your building if we don't control it properly. Remember when we were talking about the perfect wall, if you have a vapor barrier and it's inside of your thermal barrier, then you're okay. But if you have If you don't have continuous exterior insulation and vapor can work its way into your wall assembly and get to that sheathing where it's cold and it hits that sheathing, then it's going to condense, and you start having issues, moisture in your walls and stuff like that, and they need to be able to dry out. But remember, in the perfect wall, we put all of our control layers inside of our thermal control layer, and we don't have to go crazy on our vapor control. And remember, the order of importance, we're looking at water now. Water is our #1 most important control layer. Air, air can move through our wall assemblies, through cracks and stuff like that. When you have higher pressure inside, lower pressure outside, air is going to want to move through that assembly, no matter how tightly you have it wrapped. So, it's going to find a way to work its way through. And then 3 and 4, thermal and vapor. If you do your thermal control right, you don't have to go crazy with your vapor control. So yeah, moving on. So it's exciting stuff, isn't it? Are you guys pumped? Are you having a good time? Me too. Okay, so remember, when we're looking at water damage in our building, we often have multiple forms of water movement or water transport at play. So here we have bulk water. Our control layers need some maintenance over the life of the building, not only to maintain their integrity, but also just to keep them functioning. You have to replace stuff, but you also have to clean it and stuff like that. So if you have a gutter and you don't clean your gutters out, you're going to get a ton of water flowing over the gutters. And if you think about the amount of water that you're displacing in when it's raining, if you have a 2,000 square foot house, think about how much water hits the ground in that 2,000 square feet. That all has to be managed. That all has to hit your roof, which if you have a pitched roof, the area is even greater than your floor, the footprint of your building. And so that's even more water that you have to manage. So your gutters are part of your bulk moisture control, right? Your gutters are pitched, and they're gonna allow water to flow to the corner of your building, down your gutter, down your drain pipe, and into the ground and away from your house. That's a ton of water that's coming off of your roof, and when your gutters are stopped up, it's just gonna splash, it's gonna hit the ground and splash up on your, whatever material is closest to the ground at the side of your house. So here is an example, a visual example of capillary action. You see this porous material, this piece of masonry is sitting in water, and at 5 minutes, there's water being pulled up into it. Remember, the closer together those surfaces are, the higher the water can travel. So at an hour, this thing's almost 3/4 saturated. Okay, so capillary action can move a lot of water. So when we have issues, you see in the picture of this siding right here, through capillary action, water is getting pulled up into the siding, and you probably have water splashing off of the ground. And I have this problem at a well house outside of my house. When you have this, it looks like T111, this cheap siding that's not meant to be in direct contact with a lot of water all the time. First of all, you have your siding on grade. What did they think was going to happen? The ground is wet. It's pulling moisture up into the siding. You may not even have that much water splashing off the ground to do this. It could just be pulling moisture through capillary action. They painted it. That's not gonna prevent it from pulling moisture into it. It's basically like a sponge. So you have water working its way up into this stuff and rotting the wood out. If you look at the outside of a properly constructed house, you don't have wood sitting on grade unless it's pressure treated, right? You'll have some sort of a masonry element that's acting as a buffer that keeps the wood dry. Like you can have siding exposed to water, but if it stays wet all the time, it's going to rot. So that's when you do shoddy work, this is the kind of stuff that you run into. And then we have scenarios like this. Here we have an attic space, just like in grandma's house. Poor old grandma still dealing with building science issues because she didn't take building science class, or maybe she just didn't pay attention. Who knows? So, this is a pretty likely scenario. We have warm, humid air moving into the attic, and the roof deck is uninsulated. So in the winter, your roof deck is going to be cold. So, in the winter, the air inside of your house is warmer, right? And from, PV equals nRT, what is that, Boyle's law or something like that? Anybody remember that one? Yes, I'm seeing a head nod. Yes, when you have a gas with a higher temperature, and that's from physics. If you didn't have physics, maybe you haven't heard of that, and we've talked about it a little bit in this class, but if you don't know what that is, it's not going to be on the test or anything like that. But when you look at that equation, you see the relationship between pressure, volume, temperature, the number of molecules that are in a substance, and R, whatever that constant is. But when you have a warmer gas, the pressure is typically going to be higher in that gas. So when it's warmer in your house relative to outside in the winter, the pressure of the air in your house is going to be higher relative to the exterior pressure when it's colder outside. So the air in your house is going to want to move through your envelope, right? And the opposite of that is true in the summer when you're cooling your house and it's hot outside. Air is trying to work its way into your house. So, in the case of grandma's house, we have warm, humid air inside the house where the air pressure is higher. So it's trying to work its way outside of the house, and that humidity is flowing with it, and it gets into the attic and where the roof deck is cold, and it hits that roof deck, and you start getting mold, right? So here, and that's vapor diffusion. That is happening through air transport and vapor diffusion. So here is what vapor diffusion looks like. You've got all these water molecules over here moving across this seemingly solid surface, although it's not really. And over time, this water vapor is going to want to try to reach some sort of equilibrium. And, that vapor, the moisture that's in the air, is trying to go from higher concentrations to lower concentrations. So, you get high levels of humidity in your attic. You get, mold. When we're at 18%, we can get mold on the underside of the roof deck. When we're at 28%, we can get rot. If you have insulation in these engineered trusses in between your trusses or something like that, that insulation is holding moisture against that cold roof, or, well, it wouldn't be, I guess it would still be cold, yeah. So unless you have exterior insulation, continuous exterior insulation on your roof deck, which, some people do in really cold environments, but, that bad insulation can act like a sponge and hold that moisture against the underside of the roof deck. And if your roof deck can't dry out, it's eventually going to rot. So, you don't want mold in your house for obvious reasons. But when you think about all of the air currents and stuff like that, air is a fluid. It's constantly moving, right? So when you have air moving in and out of your house and you have mold in your house, mold releases spores, and that's how it propagates. So those spores are in your house. And when you have mold spores, even if you can't see surface mold, those spores are in your house. It's a health issue, but it's also an issue in that when you already have mold spores and you don't have moisture problems, when those moisture problems spring up, the mold is already there to start growing. So, it's going to grow way more quickly. And here we have a picture of a thermal imaging camera. And you can use a thermal imaging camera to look for cold spots in your envelope. You can see areas where insulation was improperly done, and you have gaps and cold spots in your envelope. You can also use it to hunt for moisture problems. When you see this sort of cold spot, that could be an indicator of a moisture problem. You could already have a moisture problem that's going to show, and that's going to show up on your thermal imaging camera. So it's a really handy tool to have when you're doing building diagnostics and envelope forensics and stuff like that. So moving on, and we're not going the full time today. I lectured for about an hour in the first class this morning, so just hang in there with me and we'll get through this and we'll finish a little bit early today. So impacts of failure. So, you know, if you're designing a house, but your crew is not up to date and doesn't know, or they're just tired because it's Friday, you know, and they don't do a good job installing these control layers. You know, you talk about contractors needing to be bonded in other classes. The homeowners have to have some form of assurance that you're going to do a good job when you build their house, and that they're not just paying you to build some piece of junk that's going to fail and have a bunch of issues. So, you know, people get sued over this stuff. There's a lot of liability with being a contractor, and if you're not doing a good job, then you can very easily get sued. And when that happens, you know, it's hard to stay in business if you're working for yourself. And if you're working for someone else, it's hard to keep your job. So, you know, this picture here in the bottom, we have some floor in what looks to be a new house. You know, I've seen scenarios like this where I've talked a lot about zip sheathing in this class. You know, if your roofers and your subs or your crew is not doing a good job installing your zip sheathing panels, you know, you spend all this money for this multi-purpose structural sheathing, you know, that has this rubberized membrane on it, and you have to tape the joints and seal them and stuff like that. When you sheathe your roof in this stuff and you walk on the tape and you compromise those tape joints and those seams, you're compromising the integrity of that control layer. So, you know, when you build a brand new house and you finish that thing and the homeowner moves in, and, you know, the water control system was not properly installed, and you know, the due care that's needed was not exercised, then, you know, your garage is flooded, and the homeowner just spent, you know, $400,000 on a brand new you know, high performance house, but their garage is full of water. They're going to be pissed, and you're going to have to go back and fix it, or they're going to sue you. So, you know, when we have moisture problems, and especially when it's in a horizontal plane, moisture can travel a long way before it will show up inside of your house. So if you have a leaking roof or a leak in between your floors or something like that, you could see moisture problems in your interior finish, and, you know, the leak be, you know, 20 feet away or something like that. So this is this can get really expensive when you're hunting down moisture issues, and, you know, having to pull off siding and pull off your finished materials to try to look for a water leak. And it's definitely something that you don't want to run into. So we try to do good design and good installation of these materials when we're building homes and commercial buildings that we're occupying. So rain control strategies. There are the 3Ds of rain control according to your book, and then we add in that last D, durability. So we have deflection, drainage, and drying. Deflection is just, lost my pen. Uh-oh, class dismissed. There it is. Deflection is just using your construction assemblies to keep rain from hitting the side of your house. So, you know, you've got all this water coming off the top of your roof, going into the gutter, but you've also got this overhang that's keeping water off the side of your house, hopefully. And then you have flashing above your windows, and flashing below your windows, and then flashing at the siding termination at the top of your masonry, your foundation wall. So, you know, these are all elements that we use that are part of deflection that we use to control the amount of moisture that hits the side of our house. So, you know, we try to keep as much water away from the side of the house and off of the ground directly next to the house as we can. You know, if we don't clean our gutters, we can have massive amounts of water hitting the ground right at the base of our house. And, you know, if you don't have your grading done properly, we need to slope our grade away from the side of the house. And notice here that they have masonry product at grade, and their siding is, you know, 8 inches or something like that above grade, so it stays nice and dry, and when it gets wet it can drain and dry. So grading is also part of our deflection. You know, you slope your grade away from the house so water will run down the grade. Water runs downhill along with other things. So, you know, we have flashing and drip edges and grading and overhangs. All of these are part of our deflection method of rain control. So, you know, if you don't have, and if you don't have this gap like we saw in, you know, if you don't have this 8 inches or whatever between the ground and your siding, like we saw in that other picture, through capillary action and splashing and stuff like that, your siding can rot out pretty easily. You know, let's see, where am I? So this is directly out of your book. You know, we're in chapter 3 again, if you like reading your book, and it helps tie all this stuff together for you. But taller buildings, when we're looking at commercial buildings and in, you know, urban settings where there are no trees, and in the case where you have no other buildings shielding that building from wind and high amounts of rain and stuff like that, and there are no overhangs that are part of your deflection strategy in that building, these buildings can be exposed to 10 times as much water as a normal 2-story suburban home with overhangs. So think about that, 10 times as much water in a commercial building with no overhangs and nothing shielding it. So those are massive amounts of water that we have to deal with and we have to design for. And here we have a link that's to whole building design guide and some moisture management strategies there. So check that out if you want to. Let's see. So we have another, you know, one of our rain control strategies. We have 3 here: drainage, storage, and exclusion. So, you know, this is part of our bulk moisture control in particular, is to control rain penetration within and through the enclosure. So, you know, the first one we're talking about storage here. We saw in the last lecture, when we have high amounts of mass in a masonry wall, we can use that mass of that wall to store water and to keep it from getting into the interior of our envelope. And remember that these structural masonry is good at forming an air barrier, it's good at damping sound, but it's not good at thermal control. So we don't see this a whole lot, but occasionally. So, you know, you have all this rain soaking in, and then the sun comes out and he's shining his rays on the wall. And, you know, as the energy from the sun hits this wall, it starts to dry the exterior surface out to the exterior. But at the same time, it's going to push a little bit of this water to the interior. And it's going to cause that water to expand, you know, inside and soak into the brick some more. But over time, the energy from the sun and that heat and stuff like that, and that moisture flow will overcome the capillary action and what have you that's pulling the water into the wall, and it'll be able to dry back out if we design our masonry, our structural masonry, for the environment that we're going to be operating the building in. So as long as there's enough mass in relation to the amount of moisture that you see in the environment, it can dry out the outside. So that is the caveat there. We have to design according to the climate in which our building is going to be operating. So areas with tons of rain, where there's a really high levels of humidity, like in the Pacific Northwest, materials may not have the opportunity to dry out, and you're going to start getting moisture inside of your building. So next we have, wait for it. Are you on the edge of your seats? Drainage. All right. So here we have the perfect wall strategy. This works based on the drainage method for rain control. So we have our first layer is cladding. That's our first layer of defense against moisture control. So rain hits and is able to drain off. Some of it's going to make its way through though, and you have this cavity on the backside, or your drainage gap. Let me switch my pen color so you can see my writing. So you have this drainage gap, which allows water to flow down this exterior surface in the drainage gap, and at the bottom you have flashing, and that's going to divert the water out and away from the wall when it hits that flashing. And notice the flashing starts at the bottom and it's overlapped going up. So it's not going behind where water would get behind it and stay. It's overlapping, and you have this mechanical control of moisture flow that's going to last a long time if we do it properly. So, you know, proper overlaps in your moisture control are key to having efficient moisture control layer, and to have proper moisture control that's going to last a long time. We also need weep holes, which is what this is, so moisture can get out, and you know, bulk moisture will flow out of these weep holes, and then, you know, through diffusion, when it stops raining, you have these gaps that it can dry through. So, you know, this method is a little bit more forgiving in terms of making mistakes in the construction assemblies and stuff like that than some other methods, but it's still, you know, there are key elements that we have to pay attention to, our laps and stuff like that, and our drainage gap, for this to function properly. And this is one of your quiz questions. Like I said, your quiz is open now. So, you know, as we go through this, you can answer your quiz questions, and at the end of the class, if you don't get any, we can talk about them. So here are some examples of drained enclosures. There's another quiz question, I believe. So we have lap siding, again, where overlapping going down, so the water will drain. It's still going to get back behind it, but we have this drainage gap behind our siding. And when you get into phase 2 of your project, which is not due until the end of October, but you know, now's a good time if you don't have too much going on, you know, take some time to rest and in between workloads, but you know, go ahead and start looking at that stuff now, so you're not waiting till the last minute to do it. You know, you shouldn't have as many issues. There's not some software that we're looking at for this portion of the submittal, but I don't want to have to push this one back like I did the last one, so go ahead and be looking at that. So anyway, we have 3 different methods of drained enclosures here. We have lap siding, we have panel cladding systems. So these are panels, and you know, you still have this gap behind the panels, and then we have a masonry veneer, which, you know, needs weep holes, and all this stuff needs flashing and a drainage gap behind it. So this is the most common method for rain control, is having this drained enclosure. And then we have exclusion, which is the last of the 3 methods for rain control. So this is also sometimes referred to as perfect rain control, or exclusion. So also referred to as perfect rain control. And in this system, you're using surfaces on the exterior of your buildings that allow for zero, none, zero, nada, I think means nothing. I don't know how to say none in Spanish. This allows for zero water to penetrate these surfaces. It's stuff like glass and curtain walls. You see this a lot in the commercial environment. So, you know, tall buildings, you'll see the exterior facade is glass. This is the method that they're using, exclusion or perfect. You know, glass is not one of those materials like masonry that's porous. It doesn't allow moisture to penetrate except at the joints. The joints in this system are the weak spots. So we seal up between these panels, these glass panels or structural glass, whatever we have, curtain walls. We seal up between these joints so water cannot penetrate the assembly. However, over time, those joints are going to wear out and you're going to have to redo them. So, you know, this type of system can last for a couple decades or so, but at some point you're going to have to redo all of those seams, all of those joints. So this is the weak point, and we're using sealant. You know, just like any other material, glass is subject to expansion and contraction when you have temperature swings, when you have thermal swings. So this stuff has to be able to move around a little bit. So you have to have proper joint sizes so that glass can expand and contract, and you have to have a sealant in between them that can move with them. It has to be flexible and not lose that adhesion when it expands and contracts. So, you know, over time, that expansion and contraction and radiation from the sun will wear out those joints. So, you know, we have structural glazing, steel clad foam panels, and then EIFS. Maybe some of you have heard about EIFS, and exterior insulation and finishing system, is I think what that stands for. But maybe you talked about that in your construction tech class, whatever they're calling that class now. So when we're dealing with joints for rain control, we have different categories that we use to identify what type of joints we have. So in this one, mass joint, you have a lot of mass here. There's a ton of sealant right here that's going to limit the amount of moisture that can pass between those joints. And then we have what's called the perfect barrier joint. And you have this row of sealant, or this strip of sealant here, that's in between these two joints, and looks like backer rod there. And then you have a drain joint. So we have backer rod here, which is just a foam, like a foam tubing that comes in big rolls, and so you don't have to use your sealant, whatever sealant you're using, and fill up that void. You shove backer rod in there and then seal over that backer rod. If you didn't do that, you're going to use a ton of sealant. It's going to get really expensive. So that makes it a little bit easier. And you get a better seal that way as well, because you've got something to push that sealant against. But see here in the middle, they've allowed for drainage. So when you have this void space behind your backer rod and moisture can get in there, you have somewhere for it to go and it can drain out. So that's, you know, the examples of different kinds of joints that we can see in rain control systems. And again, this stuff is from your book. So if you want to look more into this stuff, check out your book. So we have different methods that moisture is going to use to sort of get into our buildings. So, you know, you've got incorrect and correct up here at the top. So this is drip edge, like we saw in the drawing practicum. So through the surface tension, through, you know, that ionized water molecule with the charge that it has, like we were talking about before, and this is an example. This is what it looks like when you pull the drainage plane into your house and wrap it around your head, or the water's doing the same thing. It wants to follow whatever plane it's on. And when you put a drip edge in there, though, the water drips. That's what a drip edge does. It breaks that surface that the water wants to follow to try to move into your building. And, you know, then we have, you know, the momentum from rain can hit and splash inside of our building. So we want to put barriers that are going to stop that. And then through capillary action, when you have two surfaces that are close to one another, the water sort of pulls its way in between those two surfaces. So you put a break in your joints to where you can, you know, have a much larger distance that will break that capillary action. And then, you know, the same thing, sort of working off of surface tension here. If you detail your exterior like this, you're going to get water inside of it. So you want to drain the water away from the interior of your building, out and away. We're almost done. So here are some examples of subsill flashing. You have stuff like self-adhered membrane. You're going to come in and stick this in. You'll have some sort of a beveled piece here, or some sort of a lip. You know, remember when we were looking in that video, if you use the eye cut and you have, whoops, that doesn't matter. And you have, you're wrapping that drainage plane inside of your house. You know, if water can work behind that caulking and the sealant that you use to seal up your windows, when it gets in there, it can drain down and it can hit your flashing and then drain out of your house ideally. And this helps keep water out of your house. You'll have formable or fluid applied membranes. So this stuff, if you have a formable, it comes in sort of an accordion it's like an accordion type material, and you press it down on the window frame and then stretch it out and work it out and work it around your corners and stuff like that. And then you have pre-manufactured rigid membranes. So, you know, you've got some gap in here and you spread it out to fit your framing, and it still needs some way to adhere to that or something to fasten it. So those are just some examples of subsill flashing, which we always want to have. So some good ideas for flashing at a window. We have structural sheathing installed over a frame wall. So the first thing we're going to do is put our sheathing up. This looks a lot like a zip system diagram, but you know, this is what your phase 3 of your project is going to look like. Remember, look at that NIST Net Zero Energy Home Design Guide, and you can see some good examples of how to do that phase 3 of your project. But this is sort of what the constructability example is going to look like. You need to be able to draw something like this with the materials that you specify for your wall assembly. And remember that one, you know, the first, if you didn't get a good grade on the first part, it's only 15% of the overall grade for your control layer practicum. The last one is worth the most. So, you know, don't wait till the last minute to do that one. So, you know, you have, we're here at B, we have some beveled wood siding in the frame opening to create a slope so the water will drain out. And then we install our formable flashing at the sill, and then we install our window. It needs to be level, it needs to be plumb. This direction is level, this direction is plumb, and it needs to be square. This distance needs to be the same as this distance. If you install your shims, when you install your window and your window is out of level or out of plumb, or your shims are not properly installed and your window is out of square, over time that window is going to stop opening. The same thing is true with a door. You know, whenever you build stuff, it needs to be square, it needs to be level, it needs to be plumb. So, you know, that's something that's really important to take into consideration. And so then we have formable flashing at the sill, and notice this flashing here is installed from the bottom up, right? So we have the flashing on the sides and on the bottom installed first, and then up the sides, and then lastly at the top. If we do this out of order, you know, if we install the flashing at the top first, and then on the sides, and then on the bottom, what's going to happen? You're going to get water behind those materials, and it's, you know, it's not going to work like it's supposed to. Your moisture control layer is not going to function properly like you want it to. So then we install our tape flashing at the head, and then we install our continuous insulation. And here's just an example of what it looks like on the inside. You see the framing, the header, your king and your jack stud, and your window frame. And then, you know, prior to the window installation, you can see this subsill flashing. And then lastly, we're going to air seal around the entire perimeter of the window with sealant and backer rod, so you don't have to use quite so much sealant. So remember, you know, windows are one of the main areas where we get moisture problems, and that's one of your quiz questions. So last, in rain control strategies, we have drying. There are 3 mechanisms that we use to help a building dry out when it gets wet. And a lot of the time, you know, it's not if it's going to get wet, but when it's going to get wet. So, you know, these keys to drying are drainage, convection, and diffusion. So in draining, we need to be able to get rid of standing water. So we slope our grade away from our house, and we can have pooling water in areas like in your crawl space. So you want to have low spots in your crawl space, especially if you have a vapor barrier down like clean space or something like that. You're gonna grade your crawl so that there's a low spot in your crawl, so the water will flow to that low spot, and in that low spot you're gonna have a drain or a pump or something like that. So, you know, we also use ditching, and like I said, proper drainage slopes, grade away from your house. So next we have convection with these big fans. When we have air movement, what's moving with that air? Energy, right? So, this works really well for wet floors or carpet. Air movement and energy movement will help dry out the water, and this is through convection. We create air currents inside of our house that cycle energy, and the water picks up that energy and can evaporate. So, in old buildings back in the day, you could have airflow based on how loose your construction was, and this would help keep the interior of your building dry and help things dry out when it got wet. Now that we're sealing our buildings really tightly, this prohibits the building's ability to dry. So, now sometimes we're relying on diffusion only for the interior of our building to dry out, like in a wall assembly. And remember, you can have water vapor passing across a material that seems solid, but before people started to sort of understand when and where to use vapor barriers, people used to put a vapor barrier, and maybe some of you have seen this, some plastic sheeting on either side of a framed wall, and put vapor barriers up. And when you get moisture inside that wall, it just traps it there, and eventually your wall is going to rot out, your framing is going to rot out. So you can use a vapor barrier, but you only want to do it on the warm side, and you only want to do it on one side so your wall can dry out. But remember, in the perfect wall, if we have those control layers inside of our insulation, in cold environments, then we don't have to go crazy with our vapor control if we do a good job with our thermal control. So last slide, yay, we made it. Nope, second to last slide, I lied, sorry. So in the picture on the left, we have a house that is using individual wood planks for its siding, and this is great for structural integrity of the house, and this is great for being able to dry out. Each one of these seams, each one of these connections, these joints, is a space where air and moisture can pass through. So this is great in terms of drying, not so great in terms of energy performance, considering the implications of this design and the amount of air and the energy associated with that air can move through your envelope. So this is why some older buildings that we see seem to last so long. They seem to be so resilient, and that's why you get so many residential builders that say your house needs to be able to breathe, because they don't understand all of these building science concepts, and they don't understand the building as a system. They make one change and then you get some issue elsewhere, and they're like, oh God, that change was bad, when they're just not looking at all the other things that are at play. Your building doesn't need to breathe. The people in the building need to breathe. Your building needs to be able to dry out, but it doesn't need to breathe. We want to control when and where air is moving and where moisture is moving. And that's like the main thing that we're looking at in this class, right? It's our control layers. So the image on the right is a modern building detail, and they've used XPS for the sheathing on their envelope. When you do something like this, you'll have to use something else for structural integrity when you're dealing with racking and lateral forces, stuff like wind, and shear forces and stuff like that. So they probably got some metal strapping or some lead embracing. But when you use XPS as your sheathing, you can tape and seal the XPS, the insulation, and have a really good air barrier. You need to seal at transitions like this, and at the top at your soffit or your eaves or whatever you want to call it. And if you're sealing there and you're taping the seams, then you can do a really good job on your air control with this. But when you get nails penetrating this, you get nail holes in this stuff, then you're creating tiny little holes in which there's the potential to have a moisture leak, and this can allow water to get into the building. So when we add insulation to the cavity that sort of holds that water in there. You're relying on diffusion to help for this wall to dry out. So you're relying on moisture being able to pass through your sheetrock, which is also can be a pretty strong force to controlling airflow. You know, you're relying on diffusion for your wall to dry out when the foam is tightly sealed on the exterior. So you know, and remember when we use methods like this and we have things like vinyl wall coverings that act as a vapor barrier, then you can run into some really big issues when you're trapping water inside of your wall cavity. There, last slide. So we have different types of materials and systems that we can use for moisture control layer. The categories are, we have fluid applied membranes that we'll see on flat roofs and stuff like that. We have below grade spray applied membranes that work really well to fill in cracks, and these can move. They need to be able to move as the building settles, because your building will settle. We have house wrap materials. If you look at this house wrap material, it's sort of corrugated, it's wrinkly, and that additional surface area is allowing for pathways for the moisture to drain and to move down the face of that wrap. We have peel and stick membranes that adhere to the sheathing. And remember, you know, notice that this guy is starting at the bottom and lapping it as he goes up. So, you know, when you have peel and stick membranes, these can also double as water and air control, sometimes vapor control, depending on what you need. The loose house wraps are not as good at air control. Remember back in the day, we talked about in the last lecture, back in the day when our houses were super loose, we had a ton of air flowing through them. When we added house wrap, it was huge. It made a big difference. But now, as you know, our ideas for what a high performance building entails have changed, and we need our buildings to be tighter and tighter. House wraps are not cutting it by themselves, and we have to do a lot more stuff to make them as airtight as we want them to be. You know, and house wraps don't perform as well as these spray applied or adhesive style membranes. So we have spray foam. We saw this in the practicum. And remember, you have thermal, water, vapor, and air barrier in your spray foam. It's a little bit more expensive than you know, installing multiple barriers, but you can save time and labor cost. And you know, it's really effective as those, you know, in the way that it handles those control layers, and as it functions in terms of those control layers. So, you know, I keep talking about zip sheathing as a moisture control layer. It works well for air control if you seal it right. And, you know, remember, many things in our building can have multiple functions, right? So, and then we have these peel and stick membranes. And you know, some of this fluid applied stuff, you might need to put a primer on some of the surfaces that you're applying it to. So, you know, the devil is in the details, so they say. I don't really know what that expression means, but it sounds scary. So if you don't listen to that expression, then your building's going to fall down. But I mean, really, you know, these material systems and these different control systems have specific instructions for how to properly install them. And so when we disregard those instructions, or our subs are not aware of those instructions, then these things are, you know, they can get really expensive. So, you know, and if you spend all that money, you need to install it right. And you know, those of you who are going to be site supers, you need to make sure that your subs are installing this stuff properly and paying attention to the instructions, so that, you know, all this money that's gone into these high-tech, high-performance control assemblies is being used, and you know, it's money well spent. And you know, this stuff, if you pay attention to the details in the drawing and the instructions that are, you know, from the manufacturer, this stuff can last a long time. So that's all I have for today. Thank you, as always, for coming to class. Thanks for your attention. And does anybody have any questions? No questions. All right. So that was a perfect lecture. You understood all of it. And the pop quiz that I'm giving you right now, everybody's going to ace it. There's no pop quiz. I'm lying. Cool. Thanks for coming to class. Did everybody get your quiz questions answered? Got all that stuff? Okay. If you're not looking at your quiz and you don't understand some of the quiz questions, email me. We can talk about it or something. You have 2 quizzes due Sunday. Please start looking at your learning portfolio. I have students that are emailing me about that now, which is the perfect time to be emailing me about it, not at the last minute. So remember, that's going to be a participation credit. And if you submit something that doesn't look like you've been taking good notes, or it doesn't look like you've been working towards this final product, the end deliverable in this class, then you're not going to get full credit for participation that week. So please be looking at your learning portfolio, and when you're doing that, you can be studying some of these materials and getting, all right, you pass. A for you, Lydia. You don't even need to turn anything in. I'm just kidding. But you guys can start looking at this stuff and start studying for your exam that's coming up in the first part of October, the same time your learning portfolio check-in is, and everything's open book, open notes, so your exam's going to be hard. Be prepared. You'll have 2 tries, but all that being said, I'm not going to hold back on this exam. So if there are any issues that you're having in understanding any of these concepts, talk to me. Don't wait until the last minute and then not do well on your exam. But that being said, if you're taking good notes and you have the book, you should be fine on the exam, especially considering you have 2 attempts on this one. So I didn't say that to freak you guys out, but don't expect that it's going to be super easy. So if nobody has any questions, I hope you have a wonderful rest of your day, and go to the internship fair if you have time, and have a great weekend, and I'll see you guys on Monday.
Thanks.
Bye. I'll hang out for a minute if anybody has questions.
Yeah, can we go over the quiz questions one more time?
Yeah, which one?
Let's see, question 2 and maybe question 3.
Question 2 and 3. Let me get that pulled up.
I know question 2 is true for Windows and proper installation of controllers and the changes made in existing buildings. But I didn't know if it was true for bathrooms as well.
Yes,
what?
we saw that surface mold.
Okay, all right. Okay, yeah, number 3 was also another one that I had a question about.